Hey everyone, my name is Mike Starr, and today I'm going to talk about virtual video files. This is a technique we use at Meta to seamlessly slice, dice, split, and combine billions of videos per day. Working at Meta presents a challenge of supporting a diverse array of video products, from short-form reels and direct messaging all the way up to long-form live streaming and high-resolution Oculus content. We have to deal with a wide range of products and use cases. Because of this, I create tools and abstractions to simplify the processing of video content. Today, I'll delve into a few of these tools, starting with the concept of a virtual video file. So what exactly is a virtual video file? Imagine being able to select any set of frames from any video and instantly have access to a new video file with just those frames. Or better yet, imagine combining samples from multiple files into one single file instantaneously. This is the essence of a virtual video file. The ability to select samples from various sources and create a new video file containing exactly the data that you need instantly. Now the catch here is that I'm lying. What you get immediately is not an actual file, but a representation of the file. You can ask how big the file is, you can read any range of bytes from the file, but the file does not actually exist anywhere. Instead, every aspect of materializing this data and computing this file is done lazily. So in essence, these are virtual video files. They look and feel like real files, but they are only actually materialized upon request. So why did we build this? The short answer is storage costs. Let's take a quick journey through the history of videos at Meta. From our beginnings in 2007 to acquiring Instagram in 2012 and beyond, our video features have expanded, and so too have the amount of uploads to Facebook and Meta. But we had a problem. The storage costs were going up way faster than video uploads were, and we needed to do something about this. As it turns out, one of the biggest consumers of storage was progressive MP4s. These are files that we keep around for video players and devices that do not support dash playback. Now, while progressive gets less than 5% of the view time, it was costing us more than 10% in terms of physical storage costs. And hence, virtual video files were born. Rather than physically storing a separate copy of all of our progressive MP4s, we will create them on the fly using our dash sources and virtual video files. So here's what I'll cover today. First, we'll do a very quick crash course in MP4 files, just so that we understand the basics of what goes into the file format itself. Second, we'll look at how virtual video files are implemented and two of their practical applications. And finally, we'll look at how we integrate this technology at Meta with the world's most common encoder, ffmpeg. So very quickly, MP4 files. MP4 files are a video container or file format. A container brings organization to raw audio and video data. Containers hold both high-level information and metadata, like the number of tracks and their types, but perhaps more importantly, they also contain a data structure known as the sample table. The sample table contains the exact position, size, timestamp, and other key metadata about every frame within the video file itself. MP4 files organize the data in a tree-like structure. The file itself sits at the root, and then the nodes of the graph comprise the interior. The nodes of a graph in an MP4 file are typically called boxes or atoms. So the MDAT box, or movie data box, is just a blob containing all of the samples for either the audio or video tracks. Perhaps most importantly is the move or movie atom, which contains the movie metadata and all of the sample tables. Physically speaking, the children of any node are serialized within their parents, and so this is how we compact the actual tree-like structure into an on-disk format. And an important thing to note here is that the metadata atoms themselves actually only make up a very small portion of the overall file size. We'll come back to this in a few minutes. Now, not all MP4 files are created equal. In the real world, there are two main types that are often used. First, we have what are known as progressive MP4s. This is what you would typically have on your phone, your laptop, and it might be what you would serve a video file from an HTML page using a video tag. Progressive MP4 files typically contain both audio and video tracks together in a single file. And lastly, progressive MP4 files put the sample tables entirely within the move atom, and these have a global view of every sample within the file. By placing the sample tables in the move atom and the move atom at the front of the file, then your browser can download just a small, tiny portion of the video and then immediately be able to start playback. Now, the second common type of MP4 is known as a fragmented MP4. And this is typically what's used in dash playback for online video players. With a fragmented MP4, the sample table in the move atom is actually empty, and instead a two-level index scheme is used instead. Fragmented MP4s are broken into fragments of data, which might be 2 to 5 seconds each. An atom known as the SIDX, or segment index, contains the location of each of these fragments. And then each fragment begins with a MOOF, or movie fragment atom, which contains the location of just the local samples to that fragment. So in order to build the full sample table for a fragmented MP4, we first need to read the SIDX in order to locate the location of all of the fragments, and then we need to read the MOOF atoms in order to locate the samples within each fragment. Finally, we have what's known as remuxing. Remuxing is the process of converting from one video file format to another. Because we're not actually changing the underlying video or audio data, we're only changing the file structure itself, this process should be very fast and efficient. It's essentially a race to see how fast can you download and write the data. In reality, however, remuxing from dash to progressive runs into an interesting chicken and the egg problem. We want the move atom to be at the front of the file so that we can immediately start playing it back from our browser. But in order for the move atom to be at the front, we need to know the position of all of the samples within the file, which are after the move atom. But in order to know the position of those samples, we need to know how big is the move atom in the first place. In a naive implementation of a progressive muxer, the way you would work around this is to first write all of the samples to disk, keep track of their location, compute the move atom, and then we shuffle everything backwards so that we have space for the move atom at the front. However, this is terribly inefficient because we need to process the entire input and generate the entire output before any portion of the file is actually usable. This would clearly break down if we were trying to process a large multi-gigabyte file. And hence, this is where virtual video files come in. The concept of a virtual video file addresses the challenge of creating a progressive MP4 instantly from one or more sources without the need to actually generate the entire file. This approach not only solves our progressive storage problem, but as we'll see, unlocks and simplifies a bunch of other video processing applications too. So our goal is to implement a virtual file interface that allows us to know the size of the resultant MP4 and read data at any offset within the file. This involves creating a virtual representation of the output and then materializing the data as it's needed. Here's how we'll do that. So we begin by demuxing the source files, which is analyzing the source files, reading their sample tables, and converting this into an in-memory representation of the MP4 file. You can think of an MP4 file as a structure that has a list of tracks. Each track has metadata and a list of samples, and each sample contains its timestamp, offset, size, and whether or not it's a keyframe. An important thing to note is we'll also keep track of the file from which each sample came from so that we know how to later read the data if we're working with multiple input files. Next, we need to determine what would the sample offsets be if we were to produce the MP4. We'll start by sorting the samples in ascending order of decode timestamp so that our player can download and play back smoothly. And then we'll iterate over all of these sorted samples to determine what is their new position within an MDAT if they were to be interleaved together. With the samples laid out in the MDAT that we pretended to create, we'll now build our move atom using this layout. We can calculate what the resulting size of the move atom will be, and then adjust and account for this by adjusting the offsets of all of the samples in the MDAT, pretending that the move atom is actually at the front of the file now. And that's it. Finally, to materialize the file, we'll either do one of two things. If the read overlaps with our move atom, which is sitting in memory, we serve it out of memory directly. If the read overlaps with the MDAT atom, we'll determine what portion of which samples from which files needs to be read, and then we'll read that data directly from the sources where those samples should be coming from. That's it. We've devised a way to take samples from any number of sources and then lazily materialize a new MP4 with exactly those samples. One thing that's worth noting is that the move atom itself can be pre-computed by demuxing once and then caching this in memory. As I mentioned before, the move atom is only 1/100th of the size of the file, and so this is fairly cheap to cache not only in memory or even in a database. We also have the ability to serve read requests instantaneously, regardless of the file size itself. This is handy because it means that even for really large files that might be multiple gigabytes, we don't actually need to go and process multiple gigabytes. We only fetch the data that's being accessed. And because we're doing this all lazily, we ultimately end up saving on I/O and disk resources and can serve things instantaneously. Now, while we initially came up with the idea of a virtual file to solve the storage problem of progressive MP4s, we realized that it can actually be used to greatly simplify other processes in handling video data too. From distributed encoding to converting live videos into static VOD, virtual video files give us a powerful way to address, manipulate, and change the layout of our video data efficiently. We're going to take a closer look at two of these examples. So the first use case, which motivated us to build the technology again, is serving progressive MP4 files to players that don't support Dash. To do this, we're going to take our existing Dash sources and produce a single progressive on the fly. What we'll do is we'll construct a virtual video file, which uses one of the Dash audio and video sources for a given piece of media. We'll send a URL to our players, which will map to an HTTP server that knows how to generate this virtual video file. The players can fetch the full content size using an HTTP head request, and will return the virtual file size. And then the players can also fetch the data within the file by using HTTP byte range requests. What this means is that we can serve multi-hour, multi-gigabyte content, but only actually have to fetch the data as it's being played back in real time. The result is that we only need to store Dash encodings, and we can save big on storage costs. The second use case we'll look at is distributed encoding. Now, distributed encoding is a technique used to break a large video into smaller chunks, transcode each of those in parallel, and then stitch the results back together. Distributed encoding is super easy to conceptualize. However, the devil is in the details. Splitting and stitching together segments accurately and efficiently turns out to be very tricky, especially if you want to avoid having any single point within your system that acts as a bottleneck and we have to write everything to disk. Imagine you have a really long video. First, what we can do is analyze the source and locate where we want to make our video into chunks. For each chunk, we can then use a virtual video file to address and refer just to the samples within that chunk. This allows a remote worker to download and materialize a file that only has that portion of data and only actually needs to read that portion of data, not the entire file. And finally, after we've transcoded each of these independent chunks, we need to stitch them back together. Virtual video files can also help us here. We'll create a new virtual video file that concatenates all of the results of all of our chunks, and then we can do a streaming read and write to our network file storage so that we never actually have to materialize this file on any one local disk. So with virtual video files, we have this really powerful abstraction to refer to media data, but how do we make that easy to use? How do we fit this into the broader ecosystem of ffmpeg, which is the Swiss Army knife of processing video? For years now at Meta, the answer has been a thing called ffuse. So ffuse gets its name from the Linux kernel fuse, or file system in user space. The idea is to be able to build a custom file protocol for ffmpeg and lets us develop this file protocol outside of ffmpeg source code itself. You can think of the ffmpeg code as being the kernel then in this analogy, and then our own C++ code as being the user space component. How this works is that we have a stable, unchanging protocol in ffmpeg, which simply dynamically loads a shared object and proxies the reads, writes, seeks, and closes to our handler in the shared object. And much like Fuse proper, what this allows us to do is quickly iterate on the file protocols themselves and release them at a different cadence than ffmpeg itself. And on top of that, we can use whatever programming language we want. So when ffmpeg sees the ffuse protocol for an input or an output, it will dynamically load our shared object ffuse.so. All of the file objects operations coming from ffmpeg will then be proxied through this shared object to our C++ handler code. And then with this, we can directly connect not only ffmpeg to our internal data stores at Meta, but we can also connect it to virtual video files as described in the first part of the talk. So for example, we could leverage the ffuse connector to read our source file, but only use a subset of the frames using a virtual video file. This connector will then load up our logic for downloading just those samples. And then on the output path, we'll write directly to our blob storage and avoid having to write to local disk. ffuse does this by supporting nested protocols so that we can build and deploy one single shared object that actually has connectors for a variety of different output types and backends. At this point, then, you might be wondering, why not just use regular Fuse? So Fuse is a very interesting beast. On the one hand, it offers an attractively powerful and flexible way of thinking about files and moving data around. On the other hand, when things go wrong, they can go spectacularly wrong. And for a long time now, I've mostly bounced around and sat on the middle of this curve, loving ffuse for its simplicity and robust, easy ease of use. However, in recent years, we've finally started to shift to the right-hand side and embracing Fuse as a way to replace ffuse. So how does Fuse stack up against ffuse? I'll start by going over the cons. And the biggest one is initial upfront developer costs are much, much higher. Because Fuse, you're basically building and implementing a POSIX API, your users and your code will assume that your file system will do the right thing. And if it doesn't, it will fail in really, really bad ways. And in this case, errors are actually your best case failures. Worst case, you'll get indefinite hangs, corrupt data, poor quality of service, or spend hours debugging and scratching your head. Lastly, because everything is indirectly going through the file system, it means our tight integration with ffmpeg is lost, and it's harder to signal errors, timeouts, and that sort of thing. However, if you do pay all of these steep upfront costs and achieve a stable state of nirvana and have some sort of working Fuse file system, then the pros can start to shine. First and foremost, Fuse can be used by anything, not just ffmpeg. This means that other tools, services, and even non-video use cases can easily access not only our blob stores, but also virtual video files. Another huge benefit is being able to use the kernel page cache. With this, you can effectively use the entire available system memory and never really have to worry about because you have too much cached data. And finally, perhaps most importantly, this triggers a shift in the way that you think about files. And really, we embrace the unique philosophy that everything is a file. We can access our blob store directly, and we can even access subsets of samples within videos, just like a regular file. And by doing this, it really simplifies a lot of other pieces in our architectures. So to recap, we've talked about virtual MP4 files. These are an abstraction born out of the necessity of saving storage, but which have actually opened up and simplified a bunch of other use cases in video like distributed encoding and live to VOD. We've talked about various ways of getting data in and out of ffmpeg, from ffuse, which is tightly coupled to the ffmpeg ecosystem itself, all the way to full-blown Fuse file system, which can work with anything. And what I hope you take away from this talk is this. Investing in the right tools and APIs can allow you to hide complexity behind simple abstractions and then take on more problems faster, and with a smile on your face. Thank you.